Hi everyone, welcome to this project series in which we are modeling value at risk using three quantitative approaches, that is variance covariance method, historical method and the Monte Carlo simulation method. So in the last two videos I have walked you through the above two methods, that is the variance covariance method and the historical method, and in this video I'll walk you through the Monte Carlo simulation method. So in this video, I'll be only covering the theory part, and in my next video, I'll cover the Excel implementation of the Monte Carlo simulation method. So before going into the Excel, let's understand the theory. What is Monte Carlo first? See, Monte Carlo is a method which is used to understand and solve complex problems by running a large number of random simulations. Okay. So what is Monte Carlo? So Monte Carlo is a method which is used to understand and solve complex problems by running a large number of simulations, a large number of random simulations. So, so this concept might not be that clear with you with this definition, right? So think of it like this. Imagine you want to know the chances of winning a game, but the game is too complicated to figure out just by thinking about it. So instead, you decide to play the game thousands of times. So each time, making random moves and then see how often you win. So by looking at the result of all these simulations, you get a good idea of your chances of winning. Monte Carlo works similarly. It's like playing a game or running an experiment many times with random inputs to see what happens on an average. This helps make prediction and understand the behavior of complicated system, and that's how we use this in modeling value at risk. So in the context of quantitative finance, Monte Carlo simulation is particularly valuable for its ability to model the uncertainty and the dynamics of financial markets. So in context of quant finance, Monte Carlo simulation is particularly valuable for its ability to model uncertainty and dynamics of financial market. So you might be thinking, right? I mean, we already have two methods, right? We have the variance covariance method, then we have the historical method. So why are we using the Monte Carlo method, right? So let's, before diving into the modeling part, let's understand the advantage of using Monte Carlo. Advantage of using Monte Carlo. See, there are several advantages. First is, of course, Monte Carlo simulations can model complex financial instruments and portfolios with non-linear payoffs, such as options and derivatives. So, Monte Carlo simulations can model complex financial instruments with non-linear payoff. So, we know that non-linear payoffs are mostly for options. Second. Second reason is if you see financial returns, right? Financial returns often exhibit fat tails and skewness, deviating from the normal distribution. So, a lot of times we take an assumption, if you see the variance covariance method, we take in assumptions that the return should follow normal distribution. But what if it does not follow? If you see the period of pandemic, right? The COVID period, 2020, the year of 2020, there were times when the returns did not follow normal distribution. So in such cases, right, when let's say when the returns does not follow normal distribution, Monte Carlo is generally used because it allows you to use some alternate distribution that can capture the behavior of the assets. So the second point is financial returns can exhibit fat tails and skewness deviating from normal distribution. Deviating from normal distribution. So that's why Monte Carlo can be used. So Monte Carlo can be used to take in, or let's say to select some alternative distribution. And that's how it actually, so in this way, when you take some other distribution rather and not take the normal distribution, so this actually helps you to capture the behavior of the assets, to capture the right behavior of the assets. So this is the second reason. Third is it can actually incorporate complex correlation structures between different assets in a portfolio. So this is particularly useful in multi-asset portfolios where the correlation between assets can significantly affect the overall risk. So in this way, Monte Carlo is very beneficial. So the third point is it can incorporate complex correlation structure. See, if you remember the variance covariance method, we calculated the correlation between the stocks, and sometimes, but what if you have multi assets, right? So in such cases, like when you have different assets in your portfolio, Monte Carlo is very handy for modeling value at risk. So it can compare complex correlation structures between different assets in the portfolio. So this is particularly useful in multi-asset portfolio where the correlation between assets, the correlation between the assets can significantly affect the risk. So these are the top three reasons why we select Monte Carlo method for modeling value at risk. So if you see here, I spoke about the correlation. It can incorporate complex correlation, right? So the question is how does it incorporate, right? So the answer to that is by using Cholesky decomposition. By using Cholesky decomposition, it can incorporate complex, it can incorporate complex correlation structure. Okay. So I'll be walking you what is how to use Cholesky decomposition to basically like to calculate the correlation between the assets. So don't worry. Before that, I just want to walk you through the steps of now how to calculate a value at risk using Monte Carlo. So let's understand the steps. As you know, the first step is always common. That is collect the data. So you can basically collect the data from, let's say, Yahoo Finance, right? So you collect the data from Yahoo Finance. Second step, and this is like the most important step, use geometric Brownian motion, which is also called GBM, to simulate the stock prices. Right? So you might be thinking, what is this new term, geometric Brownian motion, right? Okay, no worries. I'll walk you through basically. So geometric Brownian motion, which is also called GBM, is a stochastic process, right? That is commonly used to model the evolution of stock price in the financial mathematics, or let's say in quant finance. So GBM, it's nothing but a stochastic process. So the word stochastic basically means random. Okay. The meaning of stochastic is nothing but random. So GBM is a stochastic process that is commonly used to model the evolution of stock price. So, some people use machine learning, some people use some other methods, right? So in quant finance specifically, we use geometric Brownian motion to model, or let's say to model the evaluation of stock price. So, so basically the equation, right? So there will be an equation, right, for the stock price. So the equation of geometric Brownian motion is, so the equation of geometric Brownian motion is okay, so dst is equal to mu st dt plus sigma st dwt, right? So now in this case, if you see this term st is nothing but the price of the asset at time t. So price of, or let's say you can say price of the asset, or in our case it is stock, right? So price of the stock at time t. So this is st. The next term is, if you see that this is mu. Mu is nothing but the expected return of the asset. Expected return of the asset. It is also called the drift component. Okay, it is also called the drift. Sigma, if you see, sigma is nothing but the volatility of the assets. The volatility of the asset return. The volatility of the asset return. ST we already covered, right? DT is nothing but small change in time, right? And now the left out term, DWT, which is like the very important term, right? DWT, DWT, it is nothing but, it is called the Wiener process. Okay. It is called the Wiener process or Brownian motion. So this part, okay, this part, this represents the randomness. And when we say stochastic, right, if you see the meaning of stochastic was nothing but random, right? So this part, this represents the randomness. Okay. So, so you might be thinking, I mean, of course, it represents randomness, but what is it, right? So let's see this term, okay? So DWT, which is also called the Wiener process, okay? Or it is also called Brownian motion, right? So what is this? Always remember, what is this? Let's say the Wiener process of Brownian motion, right? So I'll just give you an example. Imagine you are watching a tiny particle through a microscope, right? So as it moves around, let's assume that this particle moves around in a pool of water. So it moves in a jiggly or let's say erratic way because it's being bumped around by other water molecules. So now, if you track the position of this molecule, right? Or let's say if you track this position of this tiny particle, you will see a wiggling around it in a random fashion, right? So it will never stay in one spot. Instead, it will just go here or there in just random way, right? So the Wiener process is like that microscopic particle movement. It is a mathematical way to describe how something moves randomly over time. So similarly, the Wiener process, or let's say the Brownian motion, describes the random movement of particle over time. So in the world of finance or quant finance, it is used to basically model the unpredictable fluctuations in the asset price. So that is so if you see unpredictable, let's if you see fluctuations in the asset price, that is how we refer as okay, this is a this is like randomness, or this is what we say as Brownian motion. So if you see the Brownian motion, the Brownian motion describes the random movement of particle, or let's say random movement of asset. In our case, it's not the particle, it's asset, right? So it basically describes the random movement of the asset price. So this is what we say as Brownian motion. So see, we cannot use this equation directly. We need to solve this, right? So we need to solve this equation. So how will we solve it? So basically, so when you study quant finance, there is a concept which is taught in the classes of stochastic calculus, that is called ethos calculus, right? So using ethos calculus, you will solve the above equation. So when you solve the above equation, right? So you will get ST is equal to S naught EXP mu minus sigma square by 2 times T plus sigma WT. So this is what you will get when you solve this above equation, right? So now let's understand what is each term. So if you see S naught, right? S naught is nothing but the initial asset price. Okay, it's the initial asset price at time 0, at t is equal to 0. Then WT, right? So this is covered. Now WT, right? This is, as we all know, it's a Wiener process, or we can also say it's a Brownian motion, right? It's a Brownian motion at time t. Then the next term, if you see, this is nothing but the drift. As we studied earlier, drift is nothing but your expected return. And similarly, sigma is nothing but your volatility, right? Volatility term. Volatility volatility of the asset returns, right? So this is it. So let's say if you see this equation, right? If we take log on both the sides, right? So it will be log of ST is equal to log of S naught plus Now log and exponential will get cancelled, as we all know. So it will be mu minus sigma square by t plus sigma wt. Okay. So this becomes the equation, and then if yeah, so this becomes the equation that we will use for modeling the stock prices. So we can also use this equation. Sometimes people use this equation also. What they do is uh, they basically take the exponential on both the sides. So when you take exponential, log will get cancelled. So let's say if you take exponential in this side, so this will come as it is, right? So just take exponential of this. So you will get the value of ST, which is the stock price. So people can use this also. I mean, it's just the way how you want to write. So whatever way you are comfortable in, you can use this equation on. It's just how easy you feel about writing it. Okay. So let's understand. Okay. So the first step, if you remember, let me summarize again. The first step was collect the data. So using this geometric Brownian motion, using this equation, we had to simulate the stock prices, right? So once we simulate the stock prices, what's next, right? The third part is, see, if you see this specific equation, right? If you let's see you see this equation, we can calculate from the returns, right? Basically, we can calculate your standard deviation. Also, sometimes, okay, one more thing which I want to tell you. So, when you are pricing any kind of derivatives, let's say, when you are pricing any kind of derivatives, so the drift term is equal to your risk-free rate, okay? And this is also called the risk-neutral valuation. So now, if you are, this is very important assumption, right? When you are basically pricing anything, so always have to consider this drift component as your risk-free rate, right? So always remember this. So as we know, okay, so if you see this equation, so we know, okay, we know this value, what the initial value of the stock, we know the drift component, we know the volatility. The only component that we don't know is WT, right? So how will we calculate WT? So that is like the next step. That is, third is uh, basically calculate the Brownian motion. So as we know, Brownian motion is nothing but randomness. And during the start of the lecture, I told you, we basically generate a large number of random variables, right? So in this process, what we'll be doing is we'll be generating, we'll be generating a large number of random variable, a large number of So, of course, when you generate a random variable, right, it has to be generated from some kind of distribution, right? So in our case, let's assume we generate this random variable using normal distribution. Okay. So in our case, let's assume that okay, we are generating the random variable using the normal distribution. So now we have all the components, right? So now we have everything we have, right? So in that way, we can basically uh, get the value of ST, right? But there's one more catch in this. So, we always know that correlation is very important to integrate in your stock prices, right? Because one stock price, or let's say one stock can be correlated with the second stock. So in that case, what will we do in the Monte Carlo, right? So in our case, we'll be using Cholesky decomposition, right? So as I said, so use Cholesky decomposition. Okay. So if you see this method, right? If you see this method, so the random variable that it will generate, right, will be uncorrelated random variable. So Okay, so this does not contain any correlation. Okay, so that will be uncorrelated. But if you, we all know that stock prices are correlated with each other. So that is why we need to make sure like we generate correlated random variable. Okay, so we can generate correlated random variable using Cholesky decomposition. So so let's understand what is, why do we, how to basically generate this whole Cholesky decomposition, right? So first is, if you have seen my variance covariance video, you know that basically we calculate the correlation using the variance, using the covariance matrix, right? Okay, so we calculate the correlation using the covariance matrix. So once we have covariance matrix, right? So using the covariance matrix, we will generate the Cholesky decomposition matrix. Okay. So once we generate the Cholesky decomposition matrix, we'll multiply the matrix with the, we'll multiply this matrix, okay, with the uncorrelated random variable to generate correlated random variable. Okay, so this is the process. So you might be thinking, okay, like what formula are we using, right? Because so let's assume, okay, so the formula, because in my whole project series I have taken three stocks, right? So I'll be giving you the formula for three stocks, but if you have, let's say, n stocks, you can accordingly, basically take like the Cholesky decomposition for the for the n stocks, depending on how many stocks you have in your portfolio. So let's say our covariance matrix was, let's denote this by A, right? So it was something like this: A11, A12, A13, A21, A22, A23, A31, A32, A33, right? Let's assume, okay, this is your covariance matrix, right? So we know, okay, this was our stock S1, S2, S3, similarly S1, S2, S3. So when you basically when you have your covariance, so you can basically, use you can basically find out the correlation between each stocks and using the covariance matrix. So the formula that we will use to generate, let's say our Cholesky matrix is something like this, okay? L11, L okay, L11, then we have L21, L22, L31, L32, L33. So this will always remain, it will always be a lower triangular. Okay. Yeah. So this component will become 0. Okay. So now the formula for L11 is nothing but square root of A11. So whatever value we have in the covariance matrix, we'll just square root to get this L11 value. Similarly, L21 value is nothing but A21 divided by L11. So A21 is the value, you can get the value of A21 from the covariance matrix, and L11 is just what we calculated, right? Similarly, L22, right? L22 is nothing but square root of A22 minus L21 square. So again, if you see, A22 is nothing but this, and L21 square is nothing but what we just calculated. Similarly, L31 is nothing but A13 by, or A13 by L11, right? So A13 by L11 will give you L31. Similarly, L32 is nothing but 1 by L22, A23 minus L21, L31. So you can accordingly, you can base it, because A23 is again coming from this, and L21, L23, L21, L31 we are already calculated, right? This and this. So, and similarly, the last values L33 is equal to A33 minus L31 square minus L32 square. So this is how we basically, so using all these formulas, we'll get our Cholesky decomposition matrix, and then we will multiply our uncorrelated random variable with the Cholesky decomposition matrix to get our correlated random variable. So once we get this, right? So once we get this, once we do this process, right, we get our Wiener process. WT, right? We get our Wiener process. So if you see, we got this term. So if you see, we got this term. We got all the terms, right? So in this way, now you can model ST. Always remember, in Monte Carlo, if you have more than one asset, you'll always use Cholesky decomposition to first you'll generate a random variable using a normal distribution. Then you'll basically use a Cholesky decomposition and multiply with the random variable to generate a correlated random variable. So when you first basically pull, let's say when you first generate random variable in from the normal distribution, it is always uncorrelated. So you need to correlate it. How will you correlate it? Using the Cholesky decomposition. So in this way you get your stocks data, right? So now you have got your stocks data. So now the fifth is nothing but basically you calculate your returns. So you can calculate your returns using, let's say you have your, let's say value as, okay, price yesterday, oh sorry, let's say price today, whatever price of the stock you have, minus price yesterday divided by price yesterday. You can also write this as price today by price yesterday minus 1. So you can use this formula. So using the above formula, we will get multiple values for the stock, and then once we get multiple values of the stocks, right, we'll basically calculate the returns of the stocks. So once we calculate the returns, now it's very easy, right? So now this after this step, the process becomes very easy. So once you calculate your returns, arrange your returns in ascending order. Arrange your returns. So now from this step, you have to just follow historical method, nothing else. Okay. Arrange your returns in ascending order. Okay. So once you arrange your returns in ascending order, the next step is nothing but choose your confidence interval and check, or let's say, and calculate the position. So if you have not seen my historical simulation video, I will highly suggest to check that out. Like how did I calculate value at risk using historical method? So this process will become very easy for you to understand. So basically choose the confidence interval and calculate the position. So let's say I'm taking an example. Let's say we have 100 days of data, right? And I'm taking, let's say, 95% confidence interval. So when you are confident on this, your alpha or your uncertainty becomes 5%, right? So you just need to multiply your alpha with the total number of days. Let's say this is n. So just do n alpha, right? So this will give you a position. So let's say 100 into 5% is nothing but 5. So what you need to do is, wherever, since you have already arranged your returns in ascending order, right? So your returns will look something like this. Let's say negative 7%, negative 6.5%, negative 6.4%, negative 3%, negative 2.5%, negative 2%, 1%, then 1.2%, something like this, right? And as I told you in my historical video, you'll have something like this, right? So you need to give a position, right? Once you arrange an ascending order, you just write alpha, write numerically, okay, 1, 2, 3, 4. So whatever you have at your fifth position, that is your value at risk using your Monte Carlo, right? Now you multiply this with your portfolio value. So let's say we have a $1 million portfolio, right? So let's say $1 million into negative of 2.5%. So let's say we take this decimal out, we can, So this is nothing but negative of $25,000, right? So this is our value, 1 day value at risk at 95% confidence interval. Okay. So I hope you understood how did we calculate value at risk using the Monte Carlo method. I just want to summarize it. Okay. So the very first step is basically calculating the data, collecting the data. Once we have the data, we use geometric Brownian motion equation to simulate the stock prices. So the simulation can be, a large number of simulations. So once we simulate, so as I said, if let's say in this case, if you see, if we are generating, let's say 1,000 random variables, right? Let's say if we are generating 1,000 random variables, so we'll have, so if you see these are 1,000, right? So again, our stock prices will be again what? 1,000. So how many simulation we are taking, the will have similar stock prices. So basically using the geometric Brownian motion will basically simulate the stock prices, right? And once you simulate the stock prices, will have some of the other components that you need to calculate. So if you see this equation S naught is given, so you'll have to calculate WT, which is nothing but your Brownian motion or your Wiener process. So, so basically, the first thing that you do is you basically generate the random variables from the normal distribution, and those will be uncorrelated, right? So you need to multiply your uncorrelated random variable with the Cholesky decomposition, right, to get your correlated random variables. And once you get your correlated, you can basically use the GBM equation to model the stock price. So once you have the stock prices, you calculate the returns. Once you calculate your returns, arrange your returns in ascending order, choose a confidence interval and calculate the position. And whatever position your return is, right? Let's say in this case, it is negative 2.5%. Multiply that with the portfolio value. So in this case, let's assume we have taken $1 million. So that basically multiplying your portfolio value with your return at a specific position will give you value at risk at that specific confidence interval. So I hope this video have helped you. In my next video, I'll basically show you the Excel implementation of value at risk using Monte Carlo method. Thank you so much, and I'll see you in the next video.